Hey there! Today we're going to dive into a truly game-changing concept. Most students think calculus is hard because of derivatives. That's a lie. Calculus feels hard because one precalculus idea was never explained properly. And once you see it, calculus becomes obvious. We're going to call this idea the rate of change. It's the fundamental concept that connects the dots between a straight line from your algebra class and the more complex curves you'll encounter in calculus. In this video, you will be able to differentiate between average and instantaneous rates of change, learn the core mathematical formulas for both, and start seeing the underlying connection to calculus. Let's start with something you already know: the slope of a line. This is our starting point. You've probably seen this formula many times before: m equals y2 minus y1 over x2 minus x1. We can rephrase this using function notation. Let our 2 points be x1, fx1, and x2, fx2. Then the slope becomes f of x2 minus f of x1, all divided by x2 minus x1. This slope is the rate of change for a straight line. For a straight line, this rate of change, or slope, is always constant. It doesn't matter which 2 points on the line you pick. Let's work through a quick example to be sure. Consider the linear function f of x equals 2x plus 3. Let's find the slope between x equals 1 and x equals 3. First, we find the corresponding y values, or function values. F of 1 is 2 times 1 plus 3, which is 5. F of 3 is 2 times 3 plus 3, which is 9. Now we plug these into our formula. The slope m is 9 minus 5, divided by 3 minus 1. That's 4 divided by 2, which equals 2. The slope is 2. This result matches the slope we know from the equation y equals mx plus b. For a line, the rate of change is straightforward and constant. But what happens with a curve? A curve doesn't have a single constant slope. It's constantly changing. Let's use an analogy. Imagine you're driving on a winding road. Your average speed between two towns, A and B, is like the average rate of change. You take the total distance, which is the change in your position, and divide it by the total time it took, the change in time. This doesn't tell you how fast you were going at any single moment. It only tells you the overall or average rate of change over the interval. Mathematically, the average rate of change between 2 points on a curve is the slope of the straight line that connects them. This line is called a secant line. So, the formula for average rate of change is the same as the slope formula for a straight line. It's the slope of the secant line between the 2 points. This gives us a way to measure the overall change on a curve over an interval. The key here is the word interval. Let's apply this to a curve with an example. Consider the quadratic function f of x equals x squared. Let's find the average rate of change between x equals 1 and x equals 3. Remember our two objectives: differentiating average and instantaneous rates, and applying the formulas. This example focuses on the average rate. First, we find our points. When x is 1, f of 1 is 1 squared, which is 1. When x is 3, f of 3 is 3 squared, which is 9. Next, we use our formula. The average rate of change is 9 minus 1 divided by 3 minus 1. That's 8 divided by 2, which equals 4. So, the average rate of change of f of x equals x squared between x equals 1 and x equals 3 is 4. Visually, this means the secant line connecting the points 1, 1, and 3, 9 has a slope of 4. This is the average slope over that entire interval. Let's try another example with a slightly different function. Let's find the average rate of change for the function g of x equals the square root of x between x equals 4 and x equals 9. First, find the function values. G of 4 is the square root of 4, which is 2. G of 9 is the square root of 9, which is 3. Now, apply the formula. The average rate of change is g of 9 minus g of 4 divided by 9 minus 4. That gives us 1 divided by 5, or 1/5. So the average rate of change for the square root function on this interval is 1/5. You see how the process is exactly the same? Find the y-coordinates, plug them into the slope formula, and you're done. This is the core of finding an average rate of change. Okay, let's explore a more applied scenario. Imagine a ball thrown straight up. The height of the ball at any time t is given by the function h of t equals negative 16t squared plus 80t. In this context, finding the average vertical velocity is the same as finding the average rate of change of the ball's height with respect to time. Velocity is just the rate of change of position. Let's find the height at t equals 1 and t equals 4. h of 1 is negative 16 times 1 squared plus 80 times 1, which simplifies to 64 feet. H of 4 is negative 16 times 4 squared plus 80 times 4, which is negative 256 plus 320, giving us 64 feet. Now this is interesting. The ball is at the same height at 1 second and at 4 seconds. Let's see what that means for the average velocity. Using our formula, the average velocity is h of 4 minus h of 1 divided by 4 minus 1. That's 64 minus 64 divided by 3, which is 0 divided by 3. The average velocity is 0 feet per second. This makes perfect sense. Since the ball starts and ends at the same height, its total change in position over that interval is 0, so the average rate of change must also be 0. All right, it's time for some practice. Pause the video here and try these two problems on your own. Question 1. Find the average rate of change for the function f of x equals 3x squared plus 2 between x equals 0 and x equals 2. Question 2. A plant's height in centimeters over a week is modeled by the function p of t equals t cubed minus 4t squared plus 10. What was its average growth rate between day 1 and day 3? Okay, let's go over the solutions. How did you do? For question 1, we find the values at x and 0 and x2. f of 0 is 2. f of 2 is 14. The average rate of change is 14 minus 2 divided by 2 minus 0, which is 12 divided by 2, or 6. For question 2, we calculate the height at day 1 and day 3. P of 1 is 7 centimeters. P of 3 is 19 centimeters. The average growth rate is P of 3 minus P of 1 divided by 3 minus 1. That's 12 divided by 2, which is 6 centimeters per day. Wait, what's this? A negative growth rate? This is a great example of a subtle point. Average rate of change can be negative if the function is decreasing over the interval. A negative growth rate means the plant was, on average, shrinking between day 1 and day 3. Okay, we've explored average rates of change. Now for the truly exciting part, instantaneous rate of change. This is the pre-calculus idea that is the entire foundation for calculus. Let's go back to our analogy of the car. Average speed is like our average rate of change, but what is your instantaneous speed? That's what your speedometer shows you at any given moment. Graphically, the instantaneous rate of change at a point is the slope of the line that just touches the curve at that one point. This line is called a tangent line. But how do we find the slope of a line with only one point? The classic slope formula requires 2 points. This is where we get clever. We're going to start with our second line and see what happens as the 2 points get closer and closer together. Notice what happens to the slope of the secant line. As the interval shrinks, the second line gets closer and closer to becoming the tangent line. Its slope approaches the instantaneous slope at our point A. This idea of getting closer and closer is the core of a mathematical concept called a limit. It's the central idea that links the average rate of change to the instantaneous rate of change, and pre-calculus to calculus. The slope of the tangent line is the derivative in calculus. Let's put this into action. How can we find this instantaneous slope numerically? Let's use our first curve, f of x equals x squared, and try to find the slope at the specific point where x equals 1. We can't plug in a single value, but we can estimate it by taking the average rate of change on very, very small intervals around x equals 1. Let's start with a big interval, say from x01 to x3. We already calculated this. The average slope is 4. Now let's try a smaller interval from x01 to x2. We're getting closer to our target. The average slope here is f of 2 minus f of 1 over 2 minus 1. That's 2 squared minus 1 squared, which is 3. The slope has changed from 4 to 3. Let's get even closer. How about the interval from x1 to x1.1? The average slope is f of 1.1 minus f of 1 over 0.1. That's 1.1 squared minus 1 squared, all divided by 0.1. This gives us 0.21 divided by 0.1, which is 2.1. Look at the pattern. As our interval gets smaller and smaller and our second point gets closer to x is 1, the average slope is approaching a specific value. It went from 4 to 3 to 2.1. It looks like the average rates are heading towards 2. In calculus, we prove that the exact instantaneous slope at x1 for f of x2 is indeed 2. This process of getting closer is a powerful way to understand the instantaneous rate. Let's try that process with our ball-throwing function. We want to know the instantaneous vertical velocity of the ball exactly 1 second after it was thrown. We are looking for the rate of change of height at t equals 1. We'll follow the same procedure. We'll start at t1 and look at smaller and smaller intervals. h of 1, as we saw, is 64 feet. First, let's look at the interval from t1 to t2. h of 2 is 16 times 4 plus 80 times 2, which is 96 feet. The average velocity is 96 minus 64, divided by 1, which is 32 feet per second. Now let's try a smaller interval, from t1 to t1.1. h of 1.1 is approximately 67.04 feet. The average velocity is this difference in height divided by 0.1, which is approximately 30.4 feet per second. Let's get even tighter, from t1 to t1.1. The average velocity is now approximately 30.16 feet per second. We can see the pattern emerging again. As the time interval shrinks, the average velocity is getting closer and closer to 30. So we would estimate that the instantaneous velocity at t1 is 30 feet per second. Let's explore one more way to think about this that might feel more algebraic. Instead of using x1 and x2, let's pick a starting point A and a second point that is some small distance h away. We'll call this second point a plus h. Using our familiar formula, the average rate of change between A and A plus h is f of A plus h minus f of A, all divided by h. This is a pre-calculus formula, the same as our slope formula, just written differently. To get the instantaneous rate of change at A, we do the exact same thing we were doing before. We make the distance h get closer and closer to 0. In calculus notation, we write this as limit as h approaches 0. This formula, this limit as h approaches 0 of the average rate of change formula, is the definition of the derivative. It is the very engine of calculus, and as you can see, it is built entirely on the pre-calculus idea of the slope of a second line. So let's connect all this back to our main point. Calculus isn't some magic new set of rules. It's a way of solving the problem you first encountered in algebra. How do I find the slope between 2 points? Pre-calculus teaches you the slope of a line, a constant rate of change. When you get to a curve, you need a different tool. Pre-calculus gives you the second line, a tool to find the average rate of change. Calculus takes that tool, shrinks the interval to a single point, and gives you the tangent line, the tool to find the instantaneous rate of change. The derivative, the big scary word you hear about, is just the exact slope of that tangent line. That's it. It's an instantaneous rate of change. And the entire concept, from straight lines to the derivative, is founded on one simple, powerful pre-calculus idea: the rate of change. Understanding this, truly understanding it, removes all the mystery from the first half of calculus. Thank you for watching.